I'm going to talk about trees, which is a type of graph. This is a specific type of graph that's going to have no circuits and it is connected. So the first graph I have here is just one vertice. This is known as the trivial tree. And then the second graph that I have is two vertices and an edge. And then the third graph that I have is three edges and four vertices. So these are all trees looked at individually. And this is one graph. So I have three separate graphs here. With this definition and these ideas, the next definition that I'm about to give you makes perfect sense in my mind. Hopefully it will make sense in your mind. We're going to talk about a forest. A forest is a graph, and it also has no circuits. But we're dropping the connected piece. So, two vertices that are not connected could be a forest because it's two trivial trees. We could have some combination of any of these or whatever other trees that we have. And so we can put combinations of trees together and that becomes our forest. Each of these in the boxes are our graphs. Forests are graphs that are composed of trees. So that to me makes perfect sense. So it's a graph, there's no circuits, but it's allowed to not be connected. So this whole thing is one graph and it's two trees. Alright, so we're going to start to look at some theory with trees. A real quick note for applications are in computer sciences, in chemistry, where you're looking at the shape of molecular bonds, and then also in electricity. So all of those are where you can apply graph theory, and so trees can be involved in some of that. So we have a lemma here. Any tree that has more than one vertex has at least one vertex of degree 1. Theorem. In a tree, there is a unique simple path between each pair of vertices. And then this last theorem is out of this set of ideas, I think this is probably one of the most important ones, is in a tree, if you have n vertices, there are precisely n minus 1 edges. So look at this set of ideas. Can you start to think in your mind, how would you prove any of these are true? Alright, let's look at proving this lemma right here. So we're going to let G be an arbitrary tree with the set of vertices greater than 1. So we're not starting with a trivial tree here. We have to have more than one vertex. 3, 1. So it's arbitrary with the fact that it is a tree that's not trivial. Follow the algorithm. Pick a vertex. And we're going to label these with subscripts so we can keep track of which one is the vertex that we're talking about, the next vertex that we're talking about, and the same way with the edges. So we need a way to name these things, but still keep this very general. So we're going to pick vertex v sub 1, which is one of the vertices from this set of vertices for graph G. With this vertex, we are going to have an edge that's incident with this. So we're going to let E sub 1 be incident with this vertex. Well, the degree of v sub I, whatever vertex we're talking about, is greater than 1. We are going through the following steps. Alright, we're going to follow steps 1, 2, 3, and then we're going to define those steps. So our 3 steps are this. We're going to choose an edge which is incident with v sub 1. So, if we had some vertex, and maybe I can illustrate this, we have some vertex that we started with v sub 1. There has to be some edge incident with that vertex. That's going to be our e sub 1. And then at the other end of this edge, there has to be another vertex. So this is what we're going to call our vertex, which is this v sub I sequence. And so we have this. So we know we have to have at least more than one vertice. So this is basically the smallest tree that we're looking at just in this. Now, if that's all we have, we basically have what was to be proven, and we don't have to do step 3. We've terminated at this point, and we found something of degree 1 in our graph. Both of these are, in fact, degree 1. But if there's not just 2 vertices, we have the step 3, which allows us a renaming process to cycle back through. So we're going to move from e sub 1 to whatever the next edge is. So the next edge is going to be a part of that sequence. So this is e sub 2. And then I'm going to have some other vertex up here, which is going to be our v sub 3, and this renaming process here in step 3 allows us to cycle from our focus on v sub 1 to v sub 2. And so we just repeat this until, again, we come to the end of whatever our graph G is, and at that point we will have found something of degree 1 in our set of vertices. So we actually again have 2 of those. V sub 1 is a degree 1. V sub 2 is degree 2. So that's not what we're looking for. V sub 3 is degree 1 also. And so we found 2 again. So this will continue until it comes to some termination point, because we are looking at a finite graph. It has to terminate at some point. And so this lemma can be proven through this algorithm. So a nice tie-in with graph theory and algorithms is to use this process to demonstrate this lemma. All right, I want to revisit the second theorem that I had on the board that I said was, in my opinion, the most important of 3 that I had on the board. The theorem states that in a tree with n vertices, there are precisely n-1 edges. So how do we prove that? What are we looking at? So one thing that we need to understand is that this theorem talks about more trees than the last theorem talks about, because this theorem will allow us to include the trivial tree in it. We are only restricted to n vertices here, so we can start with that trivial tree of 1 vertice. So what happens if we have that? 1 vertice. So our set of vertices is equal to 1. Is this true? So n is equal to 1, because that's the order of the set of vertices. N minus 1 is equal to 0. and the number of edges in our graph of the trivial tree is in fact 0. So this case is true. So this theorem works even for the trivial tree. So can you demonstrate that case 2 works? What happens if we have a set of 2 vertices? How many edges will this graph have? And you can kind of see how this argument starts to build itself into a natural idea for the principle of mathematical induction as a proof. And so that's the technique that you probably want to look at for going ahead and finishing out the proof for this theorem. So now we need to take this next step for case K. So for any positive integer value that we plug in here, can we get this idea that the number of vertices minus 1 is going to be the value of the set of the edges here. So if the order of V is K, then the order of E should be K minus 1. We're going to assume this is true. So this is our inductive process. Now we're going to let G be a tree where the order of the set of vertices is K plus 1. So we're going from K to K plus 1. And this set of vertices is, if we look at them, if we list them from V sub 1 out to V sub H, whatever number of vertices that we have along this path. We're creating a path in G of maximal length. We want maximal length here because we want to establish these last two are going to be adjacent to each other, and so there's only one vertex adjacent to V sub H. So this means that V sub H is going to be degree 1. So that's an observation. The next thing that we're going to do in this proof is we're kind of going to break G up. And the difference between G and G prime is that we are removing V sub H and the edge incident with V sub H minus 1 and V sub H. So looking at G prime, we want to talk about a path in just G prime. All right, I talked about a theorem previously that gave us some information. And I didn't provide a proof for that. It said that there's a unique simple path between vertices in a graph. So even though we're removing a vertex and an edge, the other vertices in the subgraph are going to be connected by a simple path. So we still have the same kind of condition in G prime as we did in G. But now G prime is a graph with K vertices. G was K plus 1 vertices, and G prime has to be K vertices. In G, we also remove this edge incident, so we have one less edge in G prime than we did in G. Another observation that we can put in here now is that G has to have a set of edges of the order K. And then we are done with this proof. Cheerful calculations.